Hello everyone, and welcome to the second lecture of the Programming for Robotics course. It's 8:45, so it's time to start. My name is Tom Langhorst, and together with Edo and Professor Dr. Marco Hutter, I'm organizing this course. This is the second course, and you have started today with the deadline for exercise 1. I hope you all had fun solving the exercises and that you were able to discuss them with the TAs you were assigned to. The rest of the day will be as follows. I will be presenting the second lecture, which will be followed by an introduction to the exercises that correspond to the lecture of today. And then until 12 o'clock, you will have time to solve the exercises and work on the exercises together with your TAs for assistance. Today will be mainly about the tools and resources that you need to create your own first ROS package. First, we will talk about the typical structure of a ROS package. We will also discuss how we can use an IDE like Eclipse to integrate and program your package. Then we will discuss how we write C++ code that interacts with the ROS network, which is the ROS C++ client library. Then we will discuss some essential components to the ROS network, which are subscribers and publishers, the ROS Parameter Server, and finally a great visualization and debugging tool called RViz. Let's dive into it. ROS packages are encapsulated code with a few responsibilities. When you create a ROS package, it consists of a directory with the name of the package. It's typically a name like my point cloud processor, for example. The package then contains a number of files and directories, and these files and directories contain specialized code and configuration. A package can then depend on other packages to implement different parts of the functionality that it requires. We can use the command line tool catkin_create_package to create a skeleton for a new package. That skeleton will then contain at least the CMakeLists file and the package.xml file. We'll go through the contents of these files shortly. Now, it is good practice to separate the so-called actions, message definitions, and service definitions from your package. And why is this? This is because other packages might depend on the messages that your package provides. For example, if you have a package that does point cloud processing, you can have a separate package, which is the point cloud processor messages, that contains service definitions, message definitions, and action definitions that allow other packages to interact with the point cloud processor package without including the whole point cloud processor package. If we take a look at, in this example, package name, we see that there is a config directory. The config directory includes the parameter files, which are used in the ROS Parameter Server, which we will discuss later. Then we see the include directory. This is a typical C++ include directory, so it will contain the headers of the package, of the software that we are writing, and the libraries that we are creating. Then there will be the launch directory, which contains the ROS launch files, which describe how we want to start up nodes, how we want to compose them, and the properties and names that we want to give them. Then there is again a typical C++ folder, the source folder, which contains the source files for your libraries and executables. There is the tests directory, which contains unit tests, feature tests, which would allow you to test your package. Central to the package is the CMakeLists file and the package.xml. I will go through them in the next slides. The package.xml file tells ROS and Catkin what your package contains and contains essential metadata about your package. This includes the name of the package, which should correspond to the directory name of your package, the version number in a typical major, minor patch notation, the authors and the maintainers of the package, including their emails, and, importantly, dependencies on other packages. Now, in this case, to the right, we see a brief example of a package.xml file. It contains the name ROS package template, a version number, a description, maintainer, also a license, which you are free to choose, whatever suits you, a URL that describes where we can find this package, and the author. And then we see a few entries that explain the dependencies of the package. One thing that you will see in almost all C++ packages is the build tool depend. This indicates that we will be using the Catkin build tool to orchestrate our software. Then we will have dependencies that are related to the functionality of our package. In this case, the ROS CPP dependency, which is the ROS client library, which we will be discussing in the rest of the lecture. A standard messages dependency, which contains many interesting standard messages like strings, integers, booleans. Then we see a build depend. A build depend is different from a regular depend in the fact that it is only used during the building of your application. So when your C++ compiler is generating your binaries, it will use this dependency. However, when you are executing your package, you might not have these dependencies available. In this case, we will generate so-called message files, and therefore we need the message generation dependency. There's also the build export depend, which is the same as a build dependency, only the dependency itself will be exported as a dependency of packages that depend on this package. So it's a transitive dependency. There are more types of dependencies for different cases, and the link that you see in the bottom left will explain all these different possibilities. When you use Catkin generate package to generate a new package, you will get a standard package.xml file, which you can use to specialize to your needs. The second file that we saw in the root of the package is the CMakeLists file. The CMakeLists file is a file that instructs the CMake build system on how to build your project, how to build your executables and your libraries. The CMakeLists.txt file will consist of the following content. First of all, it will specify the so-called CMake minimum required version. In this case, I chose version 3.10, but by default, it might be version 3.0. 3.10 is shipped with Ubuntu 18.04, so that's why I chose this version. Typically, you don't have to choose this if you're not using the most bleeding edge functionality of the CMake build system. Then there is the project name. The project name should once again reflect the name of the project of the package that we gave it previously in the package.xml file and as the name of the directory containing these package files. Next, we configure the C++ standards and compile features. In this case, we use the set CMake CXX standard option to set our standard to C++ 14. By default, the standard is set to C++ 11. ROS, however, is compatible with C++ standard 14 as well. If you need newer C++ features, for example, 17 and 20, then there is no official ROS compatibility. That means you will have to separate your code that uses C++ 17 and newer features in different and separate libraries. However, this is typically not something you will do or use in in the lectures or the exercises. This is more advanced C++ usage. Next is an important step. We are going to find the different packages that we depend on. And we do that by calling find package with the catkin argument, and then the components option with a list of dependencies that we rely on. And we have to make sure that the dependencies that are listed here are also reflected in the package.xml file. We cannot have ROS dependencies here that are not in the package.xml file. And the other way around, we shouldn't add packages to the package.xml file that we do not depend on in our CMake lists. There are more functions that will be called in the typical CMake lists in ROS. And when you generate a new catkin package, you will see that this CMake lists file is actually quite long, and there is lots of content. Most of it is commented out, and it will allow you to uncomment, let's say, the parts that you need in your package. Parts that you might need are adding message files and service files and action files, or invoking the message generation for generating custom messages. There might be libraries and executables that you want to build, like a typical ROS node with add executable, or a separate library that you want to build with add library. Finally, you might want to add some tests, and there will be installation rules in the CMake lists file. Now let's go through a CMake lists example. So in this case, there is this CMakeLists.txt, it should be, I'll update that. And the first thing that we should note is that it should use the same name as the package.xml file. So in this case, we choose SMB high-level controller for the SMB high-level controller. Then we select which standard of C++ we are using, and in this case, it's C++ 11. Next, we have to list the packages on which we depend. So in this case, that's the ROS C++ client library, because we are programming in C++, and the sensor messages library, because we want to use some messages that are defined in this specific ROS package. Then is a call to the catkin package function, where we have to define a few properties of our package. First of all, we define in which folder our include files reside, and that's 9 out of 10 times the include folder. Then we can optionally define libraries that our package generates. In this case, it's commented out because we are not generating any libraries that are to be used outside of this package. But if you are, you have to specify those with the libraries property in the catkin package function call. Then we specify which dependencies, which ROS dependencies are used in this package. We do that with the Catkin depends property. In this case, it's again ROS CPP and sensor messages. So we see some repetition here, which is a necessary effect of how Catkin orchestrates the dependencies. And finally, there's an entry that would allow us to depend on non-ROS dependencies like eigen or boost. Also, this is not always the case. So in this case, it's commented out. Then we have to define the location of the header file. Again, this time we indicate CMake where we can find them. Also, we set the path to the catkin underscore include dirs, which is set by catkin package and will be pointing to the include directories of the packages that we are depending on. So in this case, at least ROS CPP and sensor messages. Now, finally, we are going to declare a executable, and the executable will be, for example, a ROS node. So it will be running standalone. The executable has to have a name, a unique name in this package. And in this case, we choose the project name variable, which just reflects SMB high-level controller. The source files, which we will use to compile this application, this executable, are listed right after the project name. In this case, we use the SMB high-level controller node, and we use the SMB high-level controller.cpp file. And finally is a very important step to link the ROS libraries to this executable as to resolve symbols that are ROS dependent, like publishers and subscribers. We do that by calling the target link libraries function. First, the first argument is the name of the executable that we just instructed CMake to make. And then the catkin underscore libraries variable, which is again set by catkin package. Now, we have edited and worked with some ROS packages, mainly on the command line by now. But an editor, an IDE like Eclipse, can provide you with very useful tools, syntax highlighting, and code analysis. So now I will quickly introduce you to the steps required to set up a project in Eclipse. First of all, we will use the command line tool catkin to instruct CMake to generate so-called Eclipse project files. And we can do that by invoking catkin build with the -g argument. And the value that we give to that is Eclipse cdt4 Unix makefiles. This practically instructs CMake to generate Eclipse files that contain details about where to find your source files, where to find the include files, and the environment variables that have to be set. Now, you might not want to add this flag to every single call to catkin build. And in that case, we can use the catkin config command to set some configuration variables. In this case, we just call catkin config and pass the same -g flag again to have catkin store that argument and use it on subsequent calls to catkin build. The Eclipse project files will be generated once you call catkin build in the workspace folder in the build directory. Now it is time to start our IDE. Eclipse is already installed on the virtual machine, so you should be able to find it easily. When you start it, it will ask you for a workspace. The default workspace should suffice in this case. You can even select the use this as the default and do not ask again option to make sure that Eclipse uses this workspace in subsequent starts. Next, we click Launch to launch the actual IDE. Then it's time to import the project that we just generated on the command line. We do that by going to File, Import, General, and then we choose the Existing Projects into Workspace option. Now we will be asked where Eclipse has to look for the project files, and you select just the Workspace folder. Next, a list will pop up with projects that are found in that Workspace folder. So in this case, it's the SMB high-level controller and also the Catkin Tools pre-built project, which we will not use. So we just select the SMB high-level controller and we click Finish. Now, to make use of the extensive code analysis features of Eclipse, we first have to make sure that Eclipse understands our project. And we do that by having Eclipse indexing it. The first step is to right-click the project in the Project Explorer tree, and then navigate to Index, and then Rebuild. Now, this might take some time, but once it's indexed, Eclipse knows how your code relates to itself and to other parts of the ROS system. From that point on, you can use code analysis features like navigating through links between implementation and definitions. There are some shortcuts which are very useful to have, to know, like the Control-click shortcut for fast navigation through related links. We can invoke auto-completion with the Control-space shortcut. And Control-B builds the workspace. Now, when you run into issues when building the workspace, you might want to rerun the catkin build command on your command line again. This might update some internal properties of your Eclipse project. You will find the source code of your project in the source directory in square brackets. There you will find the typical include directory and the source directory, which contain your C++ code. It's useful to learn the Eclipse shortcuts to quickly navigate between in your code and edit code. For example, the Control space again auto-completes your the line that you're currently working on. The Control// shortcut allows you to quickly comment and uncomment lines. These functions will help you become a fast programmer. There are other IDEs as well. Other IDEs like CLion or Vim or VS Code. And if you want to set up other IDEs, you can find instructions to do so on the ROS Wiki. However, these other IDEs are not supported during this course. So please keep using Eclipse during this course. And whenever you are working on your own projects, feel free to explore the other options that ROS provides. Now it's time to talk about actual C++ programming in ROS. And that C++ programming is done with the help of the ROS C++ client library, also called ROS CPP. The ROS CPP library contains essential components to communicate with the ROS network. We will discuss these components in the following slides. First of all, we will discuss initialization and spinning, which is the essential startup of your ROS node, and we'll do household and bookkeeping tasks. Then we will discuss what the node handle is, logging, subscribers and publishers, and parameters are other essential components to the ROS CPP library. Later, in Lecture 4, we will also discuss services, actions, and ROS time. Let's take a look at this simple Hello World CPP file, which will explain initialization and spinning in ROS. The first thing that we see is that we include the typical ROS header file, ros/ros.h. The next thing, which is required in every single ROS node, is to call the ROS init function. The ROS init function takes as a first argument the argument count, and as a second argument, the argument vector that were passed to the main function. So make sure to pass argc and argv to ROS init. The third parameter is the name of the node. And this is up to you to choose, but it would make sense to choose your package name here. What we see then is the node handle. The node handle acts as an access point to the ROS network. You can pass your node handle around in your application to give different parts of your application control over the communication with the rest of the ROS network. In this case, we use the ROS rate object class to create a rate instance where we can define a specific frequency, which we will use in the following loop. Now, in this loop, we will use a while loop here to iterate, to let the node iterate continuously. And the condition that we use in this while loop is the ROS OK function. Now, what does this ROS OK do? As long as your ROS node is supposed to be running, it will return true. But whenever a fatal error occurs, or another node in the network requests your node to stop, or the user wants to stop the node by pressing, for example, Ctrl+C, it will return false. So effectively, it's a guard that makes your node stop whenever the ROS network requests so. Then we see the ROS info macro. And this is an essential part of the ROS system, the logging part. In this case, we will use ROS info stream to output a text and the value of the variable count to the console and or to log files or the ROS out topic. More on this later. Then is an interesting call to ROS spin once. Now, ROS spin once is an essential function that you have to call whenever you are implementing a ROS node with such a loop, because ROS spin once allows the node to process incoming messages, answer to service calls, answer to signals that it gets from the ROS network. So make sure to call this ROS spin once frequently. Then we will call the sleep function. Then we will call the sleep function on the loop rate variable, which effectively makes the loop wait until the time has passed to ensure a loop rate of the specified frequency of 10 Hz. More about this node handle. So as I told, the node handle defines the access point to the rest of the ROS network. And there are 4 types of node handles. The default one, the one without any arguments passed to it, is the public node handle. And we also have a private node handle, which is specified with the tilde argument. We can also create namespace node handles and global node handles. Now, it's not recommended to use the global node handle in your ROS node, because it's easy to get to conflict with other parts of the ROS network. The node namespace will define how topics and services are resolved in the network. When you use the default node handle and you are looking for a topic called topic, then that effectively means that you will search for that topic in the namespace defined by, for example, the ROS launch file. If you use a private node handle, you will not only look for that topic in the namespace defined by the ROS launch file, but also in a sub-namespace that has the same name as your node. So in our case, it might be SMB high-level controller. We can also define an extra namespace. So in this case, we will not search only in the namespace, but also in the sub-namespace called ETH. And here we see that if we use the global node handle and we are looking for a topic called topic, that it will effectively resolve to /topic. So in that case, we are not able to use any namespaces to confine the node. An important part of the ROS CPP library is logging. Logging would allow us to input and output information about the state of our system. It's a mechanism to put human-readable text from nodes to the console or to log files. And if you have written C++ before, you will probably have used the C++ standard cout. However, we will use the ROS info and ROS warning calls instead, because these are way more flexible in this case. It would allow us to automatically log to both the console and or a log file and or the ROS out topic. There are different severity levels supported by the ROS logging macros, like info, warning, error, fatal. It supports both a printf style and a stream style formatting. The printf style is more known from C and some C++ code, whereas the stream style is a typical way of writing to the output in C++. It provides us with lots of features like conditional logging, throttled logging, delayed logging. In this table, I will show how the different types of logging invoke different outputs. So in the case of the ROS log debug, we will write to standard out, but not to standard error, to the log file and to the ROS out topic. This holds also for the info severity. The warning, error, and fatal severities, however, write to the standard error. And those messages typically pop up in a red color in your console. Here we see an example of the two types of string formatting. The first one is a printf style, and the second one is the stream style. The printf style uses character sequences to substitute parameters. In this case, %d means a numerical value. And the printf call will substitute that with the value of result. The second example shows how the same would be achieved with a stream. There we use the double angle bracket operator to append the result value to the text result. Now, if for whatever reason you do not see any output on your screen when you run a node which you launched with a launch file, you have to make sure that you have set the output to the screen, because this is not so if you don't set the output explicitly to screen, you won't see these messages. They will, however, show up in the log file. You will be able to see them in the ROS out topic, but they will not be displayed on the screen. Okay. Now, an essential part of the ROS CPP library is publishing and subscribing. Publishing and subscribing is the go-to way to communicate between nodes. And this example shows a subscriber. To the right, we see the file listener.cpp. The file first includes the typical ROS include header, ROS/ROS.h, and then a header that defines the string standard message. Now, to implement a subscriber, we define a so-called callback function. That is a function that the subscriber will call whenever it receives a message on the specified topic. In this case, we call that callback chatter callback. And we see that the argument to the callback is a so-called const reference to the standard message string. So note how a constant standard message string ampersand, which means reference, called message is the first argument to the callback. And in the callback, we just stream the value of the message to the info output. Now, in the actual main file, after the typical initialization and the definition of the node handle, we can use the node handle to subscribe to a topic. And the name of the topic that we subscribe to in this case is chatter, which is the first argument to the subscribe call on node handle. Then we have to define a queue length. The queue length is the number of messages that the subscriber can receive without overflowing. This is typically relevant when there are when the rate of receival exceeds the rate of processing the messages. However, in most cases, that should not be the case, or that might indicate an issue with the processing, with the consumption and the production of messages. We would recommend a value of in the order of 10 messages. And the third argument to the node handle subscribe call is the actual callback. In this case, it's chatter callback. Now that we've set up the subscriber, we want our node to wait for incoming messages and furthermore do nothing. So we call the ROS spin function. ROS spin is comparable to ROS spin once, only that it implements a while loop with the ROS OK call internally. So this is especially useful for reactive nodes, nodes that only reply to actions outside of the node and don't do many things out of their own. Whenever the user requests a stop or the ROS network requests a stop, ROS spin will return and the node will stop executing. Now, complementary to the subscriber is the publisher. The publisher is the way to publish messages on a topic. Again, we see that we have to initialize the node with the typical ROS init call, and we set up a node handle, nh in this case. Then we create a so-called ROS publisher. And we do that by calling the advertise function on the node handle. So instead of subscribe, we use advertise here. Then the advertise function requires a template argument, which is indicated by the angle brackets. The template argument should define the type of message that we want to send on the topic. And in this case, it is the standard message string. It should be the same type as we are receiving in the subscriber. The name of the topic is chatter. So this should be exactly the same as the name of the topic that the subscriber is subscribing to. Again, we define a ROS rate variable that defines the frequency at which we will be sending out messages in our while loop. We set up a count variable and initialize it with the value 0. And here we use the ROS OK call in the while loop again. So instead of ROS spin, we will use a while loop together with ROS spin once. We have to initialize a variable of the standard messages string type called messages, and we initialize the member variable data with the actual string that we want to store in the message. And in this case, we want to store the value hello world plus the value of the count variable. Make sure to translate that number count to a string first via the standard toString call. We also choose then to output the message that we are sending on the console. Next, we will be publishing the actual message by calling the publish method on the previously created chapter publisher with the message variable as the first argument. And now again, we call ROS spin once because the ROS node has to do housekeeping in the background. We call sleep on the loop rate again to make sure that the while loop sleeps exactly long enough to make sure that a 10 Hz rate is achieved. And we increment the count variable and repeat. This continues until one of the nodes stops, one of the nodes requests stop, and the whole ROS network is put to a rest. Now, typically in C++, you might want to do object-oriented programming. In object-oriented programming, we try to separate the responsibilities of a piece of code such that a single file and a single class is responsible for a single responsibility. In this case, we are using a structure where the MyPackage class is implementing all the necessary functionality of the node. And the MyPackage node file to the left is only very brief. It just initializes the node with the name that we define. Then it defines the node handle. And then it initializes the class that we created to implement our functionality, the so-called MyPackage class. And note that we pass the so-called node handle to this MyPackage class. As I previously explained, the node handle is the access point to the ROS network, and you can pass it around in your application to give other parts of your application the chance to control the network. By passing it to the MyPackage class, we can give MyPackage the control over our ROS node, over the communication of our ROS node. Now, MyPackage might, for example, do some LiDAR processing and relies on a specific LiDAR processing algorithm. Object-oriented programming would allow us to create a new class which would contain the actual algorithm and implement the algorithmic parts there, so that we have a nice separation between the ROS-dependent part of our package and the ROS-independent algorithmic part of our package. Note that this algorithmic part could even be separate to the package, to ROS. So it could be even released as a ROS-independent package in itself. Now, we saw how to subscribe to a topic and how to use a callback function directly. However, when you want to have a callback function that is actually a member of a class, we have to go a bit further and define, first of all, the class name and the method name, and then the argument after that is the this pointer. So that's the pointer to the specific instance of your my package. In that way, we instruct ROS to, whenever it receives a message on the specified topic, to call method name on that specific class with the instance defined by this variable. The next part is about the ROS Parameter Server. The ROS Parameter Server provides a way to store configurations centrally and to distribute them to other nodes. The ROS Parameter Server allows you to change those variables even without recompiling your code. It is nicely used for static data, such as configuration parameters, like the number of cameras that you have, the type of acquisition that you want to do, the bitrate of your video encoder, for example. The parameters can be defined in launch files or in separate YAML files. YAML is a specific format used by Yahoo that can be used to define different parameters that you want to set. In this case, this YAML file is called config.yaml, and it shows us how in a camera.left camera configuration property, we have the exposure value, which is now set to 1 for the left camera, and for the right camera, we set it to 1.1. Now, when we want to indicate to the ROS Parameter Server that we want to load this configuration YAML, we add an entry to the package launch file. We added a node entry to the package launch file earlier, where we defined the name and the package and the type. Now we want to add a child node to that called ROS Param, where we define that we want to load the configuration file that we just created. Note that we are using a relative path. We are using the find package command, where package is the name of your package, to get the relative path to your package, then the config directory and the config.yaml file. Make sure that if you are nesting a child tag in another tag, that you do not close the tag at the end of the first part, but instead use a closing tag after all the child tags. So in this case, we have a node that contains a ROS param tag, and then we indicate that we want to close that node tag again. We can access the parameter server from the command line. By calling ROS param list, we can instruct the ROS param tool to list all the parameters available in our current ROS network. We can also get parameter values with the ROS param get command and set them. However, typically we only use these ROS params for static commands. So when you change a parameter when another node is running, it will typically not adjust the value immediately, and it will require a restart. In your C++ code, you will want to retrieve the value of a parameter, and that's again where the node handle comes in. The getParam function on the node handle will allow you to retrieve a parameter by a specific name and then assign the value of that parameter to a variable that you define. This method returns true if the parameter was found and false otherwise. It's important to check what the value returns and to make sure that you do corresponding error handling. Global parameters can be accessed by preceding the path of the parameter with a slash, like in the first case. We try to get the package/camera/left/exposure parameter, and we store it in a variable called variable. Alternatively, we can use relative parameter names to get parameters that are only relative to the package. We omit the leading slash in this case. If you are using parameters, you will typically use the private node handle. That's the node handle that's initialized with a tilde, because these parameters are often only relevant to the node that you're defining. You see a brief example of how to use your node handle to get a specific parameter. So first of all, we initialize the node handle in the private namespace. Then we define a standard string variable without any content called topic. Next, we call on this node handle the getParent topic, the getParent function with the name topic, and the variable topic where we want to store the contents of the parameter. Now, if this returns false, we will invoke the ROS error macro to show an error. In this case, the error will be could not find topic parameter. If that's not the case and the getParent call was successful, then we will just show the ROS info read topic with the topic value. Those were the first, this was the first introduction to many essential parts of the ROS CPP library. There will be more parts to follow, especially in lecture 4, about service calls and actions. Another nice tool used with ROS is the RViz visualization tool. RViz is a graphical tool that allows you to show what is going on in your ROS network in a visual way. It's a 3D visualization tool specifically for ROS. It allows you to subscribe to topics and visualize what is in these topics. Now, for a string, for example, that might be not very interesting, but you can also have messages that encode point clouds or robot poses. And in those cases, it's very useful to visualize what is going on in your RViz visualization tool. It allows you to have different camera views, like orthographic and a top-down view. It's also an interactive tool to publish user information. You can save your RViz configuration to have different views, and you can then later restore them again to be able to restore the view that you previously created. It is extensible with plugins, and many of these plugins can be found on the ROS website. If you want to start RViz, then type RViz in the terminal. When you start RViz, you will see that to the left at the bottom, there is this Add button. The Add button would allow you to add plugins to your current view. And there are many plugins available. There are plugins that will visualize laser scans and transformations, maps, markers. There's only one way to really figure out, and that's to play with it yourself. When you're visualizing things in RViz, one thing to note is that the visualizations are done with respect to another frame, the so-called fixed frame. And it's important that you select a fixed frame that actually exists. Now, we will learn more about frames and transformations in a later lecture, but for now, just make sure that you click the fixed frame and you select a frame that actually exists, like the world frame or the odometry frame. Whenever RViz is facing issues, it will try to indicate that through warnings and errors. So whenever a topic is not present or a specific frame is not present, it will try to indicate these errors and warnings. When you add a plugin to Office, for example, this point cloud plugin, you will have the opportunity on the left side of your display to adjust the topic that it's listening to and to set display options like the size of the point cloud points, the shape in which they are shown, etc. Now, this is a lot of information, and you will most likely have to read up on it again whenever you are working with ROS. Luckily, the ROS documentation is extensive. For example, the wiki provides lots of information about publishing, subscribing, node handles, what happens in which situation, etc. Might you be interested at a later point to actually install ROS natively on your PC? Then take a look at the ROS installation instructions. The tutorials provide also a great way to learn more about different parts of ROS. ROS provides a huge package ecosystem with thousands of packages available. Make sure to browse through them in the future when you are creating your own ROS nodes to see what is already implemented and what not. You might be able to reuse the efforts of hundreds of other people. We also provide the ROS Best Practices repository. When you navigate to GitHub, to the LECT Robotics organization, you will find the ROS Best Practices repository. It contains a wiki with a summary of these lectures and many best practices that will be useful for you during the course of your exercises. We also provide the ROS package template. The ROS package template is a great starting point when you are creating your own packages. Finally, there are cheat sheets available online. For example, the one that is given at this Capelli link, which might be useful to have at your side to quickly navigate through the ROS ecosystem and the ROS command line utilities. This was the second lecture. It will now be time for you to go through the exercises together with Edo.
Thank you, Tom, for the presentation. Before we move on to the exercise session, are there any questions related to the lecture? Okay, then if you still think of something, feel free just to write on Piazza. Otherwise, I will then walk you through the exercise session. So can someone just, Tom, can you tell me whether you see my screen?
I do see your.
Great. Okay. So couple of points. It seems that the PDF for the exercise 2 was not uploaded correctly here. However, I have uploaded one PDF on Piazza, exercise 2. So you can just go here in live Q&A and you can then you can download this and then you can work your way through the exercise. Few more points before we move to the exercise session about the grading sessions. So I heard from some TAs that the time was a bit tight to grade everyone. And hence, in the future, we will extend the grading session and we will move the lecture to 9:15. This will be updated in the lecture slide and it will be also announced on Piazza. This means that on Friday, so the third lecture will start at 9:15 and the grading session will be from 8 in the morning until 9:15. Also, please note that there is no need to leave the grading session to go for the lecture early in case you have not been graded, simply because all of this is recorded and it will be updated on the course website. And deadline for the grading. So to show your exercise, the deadline is strict, which means that after the grading session for the respective exercise is over, there will be no more grading, which means that if you have not shown your exercise 1 today in the grading session, you will not have the opportunity anymore to do so. This is written in the lecture notes, in the lecture slides, I think slide 2, it was indicated the deadline for the exercise is before the next lecture begins. Are there any questions related to this? Okay, it will be also written on Piazza, such that in case you forget or are uncertain, you can also look it up. So then we will go through today's exercise where you will try to implement some of this stuff that Tom explained to you. And today, what you will do is you will implement your first ROS package, and you will basically make a subscriber node where you will subscribe to some topics broadcasted from the SMB robot. In the instructions, so here there's 2 ways to do this. You can do it kind of the more difficult way, where you create a catkin package from scratch. You can either use catkin create package command, or you can also maybe download our best practices template and start from there. Or if you want to take a shortcut, you can also download the zip file from the course website. So this high-level controller here, if you download this, basically here you see that there's a skeleton which is already prepared for you with the package manifest, where you can see what are the dependencies. And then there's also CMakeLists file. And then you have here include, where you basically have declaration of your class, which then you will add some functionality here that the exercise requires you to do so. You also have a source folder where there is a node and implementation of your class. So here you would put your definitions. We encourage you to implement everything. All the functionality should be implemented inside this class and not directly in the node in the main file, such that this main file, the executable, you should not touch. Once you instantiate this class, everything should be taken care of. What you should do is study a bit this package manifest and the CMakeLists. Maybe just get familiar with the structure. How do you declare your projects? What some of these lines do? How do you specify here the dependencies? Check what these commands include directories do. How do you declare here an executable? What does this target link libraries do? However, you don't have to change anything. Just study it a bit and familiarize yourself. Okay, so then I will show you, Tom has already introduced you to Eclipse. So I will also open it up and also show you another way to set up a project. So as it was written in the lecture, Eclipse generates, you can basically compile, use catkin build and generate all these project files for the Eclipse, which then it works, but it's a bit brittle and sometimes it breaks. So I will also show you another way of how to use Eclipse just as an editor and compile then directly from the command line. So I have here my workspace set up, and I will show you now how to do the same. So ideally, you have a structure where you have maybe copied in your Git folder, you have copied the common simulation stuff, the SMB common. Then you have also some stuff that it's required for the simulation to work. And then here you can also put your solution to the exercise 2. And then you will have your workspace directory, which will be then this SMB workspace. And then here you will have sim links to basically everything that is in your Git folder. So now with Eclipse, you can just make a new project. And you can just select C++ project, and you can select C++ managed build. And you can just give, so I will just give ROS course demo or whatever. This is just the project name. You can select empty project and you can click finish. It appears that I have already project with the same name in my Eclipse workspace. So I will maybe just do demo 2. Okay, don't worry if you miss any of these steps. We will upload this lecture right after on the course website. So what you can do then is you can inside, if you right click on the project, you can just say new folder. And now you will go here to advanced. And what we will do is we will point the Eclipse to our source folder inside our Catkin workspace. So you will click link to alternate location, and then you will have linked folder. So what this means is essentially that when you edit something inside Eclipse, it will also be edited inside your workspace. So your workspace is this SMB underscore workspace slash source. So you can say link, and then you can just find this in your file system, and you can say, you can select it, and then you can click open, and then you can finish. So now if you look basically inside this project here, all of the stuff that I need has been imported, like including my my SMB simulation, including some other plugins here, and including the solution of the exercise 2. There are a few more tricks to make it work nicely, such that you get autocomplete and all of the features that Eclipse can provide. So if you do right click on your project, and if you go to properties, so now we will just tweak a bit the C++ settings, which I believe we can do here. So C/C++ build settings. So first you can set the dialect of your C++ compiler, which you can put to C++11 or C++14. Let's say I will select C++14. This will then enable autocomplete for all the C++14 and 11 features like shared pointers or like make shared and stuff like this. You can then also add include paths, which will enable syntax highlighting for ROS introduced types. So the ones that you should add is, for example, eigen, since it's fairly often used, and you can just select it from your file system. Then you can navigate to eigen, select it, click open, okay, and now it's added to your include path. We can also add basically, oops, not from workspace, but from file system. We can also add the build products from our Catkin workspace, which live in Devil include. So I can also click here, open. I can add it. And I can also add stuff from ROS, which lives in, where do you live? Opt, ROS, noetic, include. So I add this folder here. You can click OK, and then you can click apply and close. So now the Eclipse asks you to rebuild the index. So you can say yes. And now you will see here in the bottom right corner that C++ index is being built. And this is the feature that enables you like auto completion and all of this syntax. Actually, syntax highlighting is over there, but auto completion is enabled when you build your index in your workspace. So this now might take some time to build. So actually, I will just stop it and use my old workspace. And yes, Eclipse seems to be a bit slow. So I saw one of the questions is why do we use Eclipse in the course? It's simply because Catkin build system can generate you all of these files, and because it's free. But you can use whatever you want for editing. Since you mainly will be building from command line, you can use whatever you like. Like some people use CLion, there's also people that use Sublime. You can use Vim or Emacs or whatever you like. So let's say hopefully here my syntax highlighting will still work. So if I go here in this high-level controller node, you can just start typing like this. And then if you press Control space, it basically fills the syntax for you. So it recognized that this, when I just type S, it offers me a bunch of suggestions of what I might want to type. But if I write SMB, so now it's telling me, okay, you can either reference this object here, or maybe you want to reference this namespace, and then you can just press enter to complete. And this is then how you can navigate much faster through the code. It also works for functions. So for example, if I include just eigen here, and now if I instantiate some of the eigen types, so it already offers me the auto completion. But let's say I want to instantiate the dynamically allocated matrix of doubles. And now if I type matrix, if I reference this variable and put a dot, I can again press Control space, and it wants to auto-complete any function that basically is defined, or any method that is defined for this class. So if I start typing, it also does the search for me. For example, I could set this matrix now to identity, or I could do maths. I could compute a norm, which already it gives me auto completion for all this stuff. So with these, like with auto completion, it's a bit easier to code in the beginning, but eventually you will learn most of this stuff by heart, and then you will be much freer in the choice of your editor. Okay, so this would be related to Eclipse. Are there any questions here? Okay, I see nothing. So then we'll just walk through the exercise. So I will build my, I will, I guess, clean my workspace, because I don't know what was the last thing I built. And then I can build the SMB high-level controller, which is what you have to write in this exercise. So this will now maybe take a bit, but we can also just go through other points. Why is my, there we go. Okay, so in this exercise, you will notice there's kind of 2 bonus tasks that you can solve in order to get extra points. So from this exercise, then you can get 120 points. However, from the exercises, you can get at most 500%. So you cannot basically transfer these points to the exam. There's 5 exercises. I guess first one was 100%, this one is 120. So, but at most you can get 500%. I will not detailedly explain these points. These are if you have extra time or if you're interested or just bored or whatever, you can try to play with these. Okay, so now let's check my workspace. How is it doing? It's still building. And then I will run the exercise for you. One important thing is here you have to subscribe to this scan topic. You can use all the tools from this lecture and the previous lecture to inspect the notes, see which topics are they publishing on, to see who is publishing what, which should help you to solve the exercise. And then, yeah, this is, I guess, pretty much it. So make sure you use parameter files and do not hard code your, I believe, topic name and topic queue size inside the code. So just make these parameters configurable in the config file. And now my workspace is done. So hopefully if we source it now, we should be able to launch it. SMB high-level controller launch. Okay. Okay, so here inside my RVis, there's a bunch of stuff that you don't have to do now. So I will just show you how to do everything from scratch. So first you have to visualize your laser scan topic, which you can do by clicking here, add in the bottom left corner in RVis. And then you can either say by display type, laser scan, and then manually write out the topic, or you can just click by topic, and then you can select here laser scan, which is already published. And now we still don't see any points, but I will show you why. So if you look in Gazebo, how this robot looks like, this here is the front side of the robot. So you can tell this, it has kind of these like 2 eyes where normally cameras would be, but we don't have them enabled here for the ROS course. And then this is the back of the robot with bunch of different, with bunch of holes where normally connectors would be. So the reason you don't see anything in the laser scan is simply because there's nothing in front of the robot, and the robot is only scanning kind of forward. And the way you can solve this is either by adding some objects in front of the robot, or you can also use your teleop twist keyboard node, and you can steer the robot towards this goalpost, which will then become, basically you have to turn it 180 degrees. So now I should see some stuff inside the RVis. So this is my laser scan. And now you can basically, I think one of the tasks is you have to play a bit with the size of these points. You can also change their color. So if we put color transformer, if we just say that we want flat color, we can maybe put them to, I don't know, let's say green, and now stuff shows up green. It's also important that you put this fixed frame to odometry, and not to something else. For example, if I put it to map, you can see that now the laser scan is gone. So if you do not see stuff, go here and just change this to bottom. And then you should be able to see stuff. And so now if I start moving the robot, for example, if I start turning, you can see that now these scans move, and this is because the robot is now turning. So now I see here the goalpost, and now I see again these objects that I have added. And then I believe this is pretty much it from the exercise. There's also some stuff that you have to print inside the terminal. But I guess this should all be written here. I think this concludes then. This concludes the exercise intro. Are there any questions? Okay, if not, then you can now start working on your exercises. The TAs will be with you from 10, or they should already be in the exercise rooms. So then have fun, everyone, and good luck. I will now, if there are no further questions, I will finish this lecture. Good job.